Okay, good morning. Let's get started. We have two more lectures to go, right? So now I think last time we already talked about the fibers, muscle fibers, right? And show you guys a table. So again, try to remember first the mitochondria content first, and focusing on the type 1 and type 2X. It's very different, almost opposite, fibers in terms of metabolism. Try start to remember, start with mitochondrial content, and then you can expand it in other information, right, in terms of glycogen content and triglyceride content, aerobic and anaerobic capabilities, and oxidative capacity or glycolytic capacity, right? Now let's talk about this more and in more details. The type of muscle fibers, because it's actually very important for us to understand better how energy fuels are used by muscle fibers during exercise. How can we improve the exercise performance? So type 1 fibers is the red fibers, right? And the slow and twitch fibers. It has a higher mitochondrial content, so this type 1 fibers has a higher oxidative capacity, so be able to metabolize, able to do the aerobic metabolism, right? Especially for the fat oxidation. And this type of fibers is suited to perform endurance exercise, for example, marathon and long-term exercise. And question here, how is glucose metabolized in the type 1 fibers? Glycolysis, partial glycolysis, oxidation, or complete oxidation in type 1 should be complete, right? Because it has a lot of mitochondria, so you're able to do the oxidative metabolism, able to do most of the glucose, be able to completely oxidize or produce ATPs in the type 1 fibers. And type 2A fibers is the fast twitch and the moderate oxidative capacity. I mentioned the type 2A kind of intermediate, between type 1 and type 2X. So type 2A fibers are able to do both aerobic and anaerobic metabolism. So can oxidize fatty acids, can utilize fatty acids, and also has a higher glycolytic capacity. So type 2A fibers can also does utilize glucose, but does partial oxidize, right? So they can do the type 2A fibers can do both aerobic and anaerobic metabolism, and can be used to perform middle distance running and swimming, this type of exercise, right? And type 2X is just opposite to the type 1. It is actually fast twitch and low, because they have a low mitochondrial content. So the type 2X basically has a low oxidative capacity and very high glycolytic capacity. So usually type 2X does the anaerobic metabolism and used to perform the very short-term exercise, for example, just 100-meter sprinting, right? And it takes 10 seconds. So this type of a short-term exercise, usually you use type 2X fibers. And how is the glucose metabolized in type 2X fibers? Glycolysis, right? usually partial oxidation glycolysis. So type 2X fibers usually can produce a lot of lactate, and lactate is it causes the fatigue, the muscle fatigue. So it can significantly affect the exercise performance. And in a prolonged exercise at like 60 to 75% of maximum oxygen consumption, which we're going to describe later, details about VO2 max. It's used to determine the exercise intensity, right? So during the prolonged exercise, for example, marathon, so type 1 fibers and type 2A fibers, both type 1 and type 2A fibers are recruited during the early stage of exercise. So these two type of fibers be able to do the aerobic metabolism, right? And as the exercise prolongs, the type 2X fibers can also be recruited and activated to maintain the same intensity, but you know that type 2X fibers usually perform the anaerobic metabolism, right, and produce the lactate. So as the exercise prolonged, you feel like lactate production will be increased and you're getting kind of fatigue. And type 2 fibers, yeah, is the reason for muscle fatigue that produce because of it produces the lactic acid due to the anaerobic metabolism, right, glycolysis. Okay, so in terms of type of exercise, we already described at the very beginning. We usually have two different types of exercise, aerobic and anaerobic exercise. So aerobic exercise basically is a moderate intensity undertaken for a long duration and usually utilize oxygen, right, for energy producing process. So aerobic exercise usually utilize type 1 and the type 2A fibers, and to do the oxidative metabolism requires oxygen for producing energy. So the example for aerobic exercise is marathon, right? And anaerobic exercise usually is the short-term and high energy required exercise. For example, for anaerobic exercise is 100-meter sprinting. Right? It takes very short period of time, just 10 seconds. And this type of exercise is the anaerobic exercise. Why? Very short-term exercise is anaerobic. Under what conditions, our body does the anaerobic metabolism? Thinking about when we don't have oxygen, right? So we need to produce ATPs, but we can oxidize nutrients in the mitochondria without oxygen. So with no oxygen, then the glucose has to go just the partial oxidation, glycolysis, right? So the reason because of oxygen cannot be transported quickly enough to the muscle, right, to provide increased oxygen needs during this intensive exercise. So that's why under the relatively lacking oxygen conditions, that fiber has to utilize glucose for partial oxidation or glycolysis, right? So this is the main reason why this type of short-term exercise utilize anaerobic metabolism for energy. Now exercise intensity. So how we define exercise intensity? So exercise intensity is determined by the muscle contraction cycles per unit of time. So the higher the exercise intensity, the more contraction cycles are needed per unit of time, right? So depend on how how much the contraction cycle is needed, and also more ATPs that need to be synthesized per unit of time in order to meet the energy requirement, right, for the muscle contraction, and also more fuels are needed to be oxidized. So the rate of ATP synthesis and fuel oxidation in muscle are increased during exercise because of the contraction cycles increase, right? So the intensity is depend on the contraction cycles per unit of time. Now the other concept about the VO2 max and how we measure exercise intensity. As muscle contraction cycles increase and need more ATPs, right, and need more oxidation of energy fuels, so that process will require oxygen. So higher exercise intensity requires more oxygen. So we usually measure the oxygen consumption for the exercise intensity, right? So VO2 max, the maximum volume of oxygen consumption is the person's maximum aerobic capacity, right, defined as 100%. So usually we don't use 100% maximum, but just the maximum capacity that we can do, but usually use less than 100%. So for example, the energy expenditure, try to remember this percentage related to the different levels of intensity of exercise, right? So low intensity exercise, for example, fast walk, and this type of exercise we only use 20% of our maximum oxygen capacity, and moderate intensity for faster jog. This type of exercise uses 60% of VO2 max. And high intensity exercise, for example, 2 to 3 hour marathon running, and we usually use 80% of our maximum oxygen capacity, right? So oxygen consumption is also linearly related to energy expenditure, which also makes sense, right? If we try to burn or oxidize more nutrients, fat or carbohydrates, definitely will need more oxygen, right? So much oxygen positive related to the energy expenditure. And greater consumption of oxygen is also related to the greater intensity exercise, right? We already described, more muscle contraction cycles, and we need more energy and need more oxygen for producing energies, right? And training can increase oxygen consumption, which is very important. We're going to talk about later, because during exercise, we not only just use glucose, we need to use fatty acids. So fatty acids will be also a very important energy fuel for ATP production, which also the capacity of the fat utilization is very important, can affect the exercise performance. So training, you can increase our body to utilize the fatty acids that, and increase oxygen consumption. And VO2 max can be increased by 15 to 20% with training. So after training, if we compare untrained person that a trained person usually can increase oxygen consumption by 15 to 20%, which is good, right? You can increase, the ability or capacity of fat oxidation. Now, fuel utilization during the resting state, is pretty much similar to what we already talked about in earlier sections, right? Just in resting condition, the muscle usually oxidize a mixture of a carbohydrate, fat, and the muscle be able to utilize carbohydrate and fat depending on the physiological condition. Remember, in the fat condition, muscle usually utilize more glucose as energy because of the availability, right, of glucose from the diet. And during the fasting condition, muscle start to use fatty acids as alternative fuel because of limited sources of glucose. And other thing is important that is different from the exercise. If we compare resting state to the exercise conditions, the utilization of a fuel, the sources of a fuel utilization is a little bit different. For example, in the resting conditions, the blood-borne fuels are the primary sources. For example, blood glucose can be from diet or can be from the glycogen breakdown from the liver, right? So the blood-borne fuels are the most important, and fatty acids can be released from adipose tissue during fasting condition. But the muscle glycogen or intracellular triglyceride, muscle intracellular triglyceride are not the important energy fuel during the resting condition, right? So again, resting condition, muscle mostly utilize the blood-borne fuels, which initially from the diet or from the liver glycogen breakdown for glucose or fatty acids, released from the adipose tissue, but not much glycogen intracellular, muscle glycogen, and muscle intracellular triglyceride, right? And fuel utilization scales muscle during exercise. So during exercise, muscle can utilize multiple energy fuels, including carbohydrate, fat, and the muscle-creating phosphate, right? So and also the sources of the glucose or fat are also a little bit different. In addition to the blood-borne glucose or fatty acids, muscle can also utilize muscle glycogen, right, which is very important sources of glucose for muscle during exercise. And for the fat, in addition to the free fatty acids pick up, from the circulation or triglyceride, and intramuscular triglyceride is also important sources of fatty acids for muscle use during exercise. And muscle-creating phosphate is important energy fuel for anaerobic exercise, right? Anaerobic exercise. We're going to talk more about this later. So energy expenditure is increased in muscle during exercise because of the availability of carbohydrate fatty acids is increased, right? So we know that kind of hormonal levels are changed that can regulate the availability of carbohydrate fatty acids, and also the ability of muscle to utilize both fat and carbohydrate also increase. So that can increase the energy expenditure and provide more energy for use during the exercise. And energy cost of working muscle, so how energy is produced basically from ATPs, right? So we need to break down ATP to release energy from ATP molecules. So muscle contraction requires energy from hydrolysis of ATP by several different ATPase, right? The potassium, calcium, ATPase, and actually the body uses only half of the skeletal muscle mass for running marathon. So not all the muscle involved exercise during marathon. Only half of muscle by the body in the body and used for marathon. And most of ATP required for marathon is produced by aerobic oxidation of carbohydrate and fat, right? Because marathon is considered the aerobic metabolism. And for 100 sprint meter, 100 meter sprinting, because this is anaerobic metabolism, right? So ATP for 100 meter sprinting usually comes from the creatine phosphate and glycogen, and glucose is only partial oxidized, right? Anaerobic glycolysis. And here just show you the ATP energy produced from ATP, the process. So ATP can be made from oxidation of glucose to fatty acids, right? And this is the ATPase. 3 different types of ATPase can break down the phosphor bond and to release energies from ATP molecules. And ATP required for muscle fiber shortening and movement, and also polarization, depolarization of muscle cell membrane, right, in response to a nerve signal, so then can stimulate muscle contraction. And also muscle contraction requires calcium, right? So calcium released from sarcoplasmic reticulum into the cytoplasma is also require energy. So all these activities, and require energies for muscle contractions. And sources of carbohydrate and fat for oxidation in skeletal muscle. So during the aerobic exercise, right? So again, the different type of exercise, aerobic and anaerobic exercise require different type of energy fuels, right? We already noticed that, right? So now let's talk about the aerobic exercise. So during aerobic exercise, the glucose and fatty acid are needed, right, for making ATPs. And glucose basically have 2 sources. One is the blood-borne glucose. It is initially from diet glucose and liver glycogen breakdown, right? And also muscle glycogen is very important sources of glucose for aerobic exercise. And fatty acids also have blood-borne fatty acids from dietary lipids and also from the breakdown of triglyceride in the adipose tissue. And triglyceride in the lipoproteins, for example, VLDL, and also also is one of the sources of fatty acids. And intramuscular triglyceride can also break down to release fatty acids and utilize within the muscle, right, for the energy production. And this diagram gives us a sort of summary, or maybe better view of the energy glucose sources, right, during the exercise. So 3 sources of glucose, right? One is from the diet, the circulating glucose from the diet, and the second, glucose in the circulation from the glycogen breakdown, right? And the third source of the glucose is the muscle glycogen, can also break down to, and to do the aerobic metabolism for ATP production. So there's some questions. Where does glucose used in muscle come from during the aerobic exercise? Muscle glycogen, right? Muscle glycogen is a major source of a carbohydrate during exercise, though of course from the circulating, right, glucose. And how is glucose metabolized during aerobic exercise? I listed here the different type of fibers. So type 1 and type 2A, these two type fibers are able to do aerobic metabolism, right, because of their high mitochondrial content. So these two type of fibers can do aerobic metabolism of glucose. So glucose is aerobically metabolized in type 1 and the type 2A fibers during exercise, right? And what about in type 2X fibers? And although this is just, for the anaerobic metabolism, not belong to this category, but I just, remind you guys that type 2 fibers, glucose in type 2 fibers only goes partial oxidation, anaerobic metabolism, right? So anaerobic glycolysis. Okay. Now sources of fatty acids for oxidation during aerobic exercise. Three sources, right? One is from the hydrolysis of triglyceride in adipose tissue. During the exercise, the catecholamine levels is increased, right? So catecholamine, like epinephrine or epinephrine, and are the important hormones that can stimulate lipolysis to push the hydrolysis of triglyceride and release fatty acids. So fatty acids levels increase during exercise and then can be picked up by the muscle and utilized, oxidized aerobically in the muscle and to produce ATPs, right? So this is one sources of fatty acids. And secondly is the fatty acids from triglyceride, which released from liver, right? And this source of fatty acids can also be used by the muscle for energy. And lastly, the intramuscular triglyceride. So triglyceride also is stored in the muscle, right? So this intramuscular triglyceride can also be broken down to fatty acids and utilized as energy fuels. So three sources of fatty acids that can be utilized by muscle during exercise, during aerobic exercise. So the question I wanted to ask you, so do you think the anaerobic exercise, for example, 100 meter sprinting type exercise, muscle utilize fatty acids? No, right? Yeah, thank you. So the muscle not able to utilize fatty acid because of oxygen or lacking oxygen. So during aerobic exercise. So aerobic exercise, again, only utilize creatine phosphate and glucose. And this glucose only from the muscle glycogen, right? And liver glycogen is not the major contributor to glucose utilized in the anaerobic metabolism muscle fiber because of also breakdown liver glycogen and deliver it to the muscle also requires time, right? So it's also not quick enough. So muscle glycogen is the main sources of glucose during anaerobic exercise. Right? So fuel utilization of fuel metabolism and in aerobic exercise. Increased oxygen uptake for TCA cycles and fatty acid oxidation in mitochondria, right, is required for aerobic metabolism. So aerobic metabolism requires oxygen and the mitochondrial oxidation, right? So that means the fiber has to have a mitochondria, or the high intensity of a mitochondria. And for aerobic metabolism occur, there are actually kind of a physiologic adaptation is needed in order to make efficient aerobic metabolism during exercise, right? So the following three things that are happening during the exercise that can, adapt the body to increase the oxygen consumption, to increase the aerobic metabolism. For example, during the exercise, the heart rate and volume, is increased, right? And also breathing rate is increased, and blood flow to muscles also increase. So all these adaptations can increase oxygen delivery to the muscle for an oxidation, right? For oxidative metabolism. So these adaptations are needed to increase oxygen consumption for the aerobic exercise during exercise. And changes in the fuel metabolism. May no muscle be able to utilize fatty acids and carbohydrate, but during the different stage of the exercise, the utilization of fat and carbohydrate actually is a little bit different. So for example, from the low to moderate to high intensity exercise, muscle is able to utilize carbohydrate gradually, the utilization of carbohydrate gradually increase from low to moderate and to high intensity exercise, right? But for the fat utilization, it's quite different. So from low to moderate exercise, the fat utilization increase in the muscle, right? But start from the moderate to high intensity, as the exercise intensity increase further, the fat utilization start to decrease, right? We have a reason why, fat utilization decrease. So that makes the carbohydrate storage or muscle glycogen store is very important for exercise, because during the later stage, the high intensity exercise, the fat utilization, the capacity is decreased. That means, you rely on the carbohydrate stores. So if we have more carbohydrate stores, then we can less rely on the fat utilization, because fat utilization decreases, right? So we still be able to perform if we have enough glycogen be used for energy. And this is slide, I think it's talk about the concentration of fuel in the healthy young male subject in response to 2 hours of exercise at 70% VO2 max, right? And then followed by 1 hour recovery. So I think this probably give us some better idea how energy fuels utilized during exercise, and 2 hours exercise pretty much like a marathon, right? So you can see the glucose level is actually decreased during the 2 hour exercise, right? And the lactate levels increase and then remain at high level, right, in the circulation, which makes sense, right? You exercise, you utilize a lot of glucose and also produce a lot of lactate. And fatty acids level and glycerol level is also increased during the 2 hours exercise, and triglyceride level remain pretty much constant, right? And during the 1 hour recovery period, that you can see the glucose start increase back to the the normal range, and then fatty acids keep going up, and lactate declined, and glycerol also decreased, right? So this 1 hour recovery period, that the body, the muscles still utilize fatty acids even more, fatty acids. Why our body does that? During the recovery period, why we utilize more fatty acids? Any thought? Okay, we're going to talk about later, right? So during this 1 hour recovery, we wanted to spare glucose, because after 2 hour running, the muscle glycogen almost completely gone, right? So we need to re-synthesize glycogen to rebuild muscle glycogen. So we try to spare glucose for the glycogen storage. So that's the reason why we use more fatty acids, right, as energy during the recovery period. And lower, decreased lactate and glycerol, possibly due to the increased also gluconeogenesis for glycogen storage, right? So this may be related to that activity. Now, how about hormonal levels during the exercise? How hormonal levels change during the exercise and 1 hour recovery period? So as insulin levels decrease, which associate with decreased glucose level, right? During exercise, muscle uptake a lot of glucose and utilize as energy, so blood glucose level goes down during exercise, which also have a less stimulation for insulin secretion, so insulin level also goes down. But glucagon level is increased, right, to try to make more glucose, gluconeogenesis, or break down the glycogen. So the glucagon levels increase. And most importantly, the epinephrine, catecholamine levels actually increase a lot during the exercise. Why we need to have an increased epinephrine levels, catecholamine? What catecholamine hormones does in terms of the energy? Yeah, so break down fatty acids, triglyceride, release fatty acids, right? Very good. So increase the epinephrine can stimulate the lipolysis and release fatty acid from triglyceride in the adipose tissue, right? And that's needed for energy production in the muscle. So recovery period, and insulin levels start to increase, and glucagon level start to decrease, and catecholamine level is actually decreased, right? Okay. Yeah, so I think we pretty much covered this, right? The circulating hormone levels, the insulin decrease, glucagon increase, and catecholamine levels also increase. And blood flow to muscle should be increased, right? To allow more oxygen being delivered from the lung to the muscle for oxidation of the nutrients. And the muscle contraction increase. An important thing is that AMP-ATP ratio increase because a lot of ATP being break down to AMP, right? So AMP levels increase and ATP levels decrease. That causing the increased AMP to ATP ratio. And this change, this ratio increase is very important, can stimulate the AMPK. This is a very important enzyme, kinase, remember, right? It can regulate the marino-CoA production and regulates the fatty acid transport and oxidation. So AMPK activity can be activated, can stimulate the more fatty acids transported from cytosol to mitochondria, right? And the pathway, remember that, AMPK can activate ACC, right? The phosphorylated ACC can decrease ACC activity. And ACC is important enzyme for the formation of marino-CoA. And marino-CoA is very important molecules and inhibits CPT1, right, the enzyme on the mitochondrial membrane. Remember this. And because of marino-CoA level decrease, so you have a less inhibition, so CPT1 enzyme activity goes up, so it can transport more fatty acids from cytosol into mitochondria and for oxidation and energy production. So this is sort of one of the regulating mechanisms, why fat oxidation is increased during exercise. And it also can increase uptake of glucose, right? Remember the AMPK also regulates GLUT4 translocation to muscle cell surface. Okay. All right, so so during the exercise from rest to moderate to high intensity exercise, the glucose uptake is increased, right? Because of exercise can activate AMPK levels, right? And increase GLUT4 translocation. So that is the reason why blood glucose level goes down, right? You have a more uptake by muscle and utilized for energy. And liver glycogen breakdown is also increased because of a glucagon levels increase, right? It can stimulate glycogen breakdown in the liver. And the exogenous glucose oxidation is increased, and muscle glycogen store also be breakdown, right? To release the glucose for energy use. This something happening during the initiation of the exercise, right? So basically utilize more glucose, right? Either from the circulation uptake into the muscle or from liver glycogen breakdown or muscle glycogen breakdown. I guess maybe I will just finish this slide and then we'll take a break. So muscle glycogen store, as I mentioned, it can influence the utilization of fat versus a carbohydrate during moderate, particularly the high intensity exercise. Remember I mentioned that during the high intensity exercise, our body utilize fatty acids. The ability of utilize fatty acids actually decrease, right? So how much glycogen, muscle glycogen store can influence the utilization of fat versus carbohydrate. So this sort of just in general process. For example, muscle glycogen depletion uses more fat, right? If we don't have enough muscle glycogen store, that we have to utilize more fat during the later stage of exercise, right? Because of the low pyruvate dehydrogenase activity. If we don't have much glucose available from muscle glycogen, then the pyruvate formation will be reduced, right? Pyruvate actually is generated from glycolysis, glucose glycolysis. So this will decrease the pyruvate dehydrogenase activities. And then we have less acetyl-CoA produced, right? So acetyl-CoA levels decrease, and of course you have less marino-CoA is formed. So marino-CoA, as I mentioned, is very important, right? Regulates shared fatty acid transporter. So lower marino-CoA levels will allow the more fatty acids being transported to mitochondria for oxidation, right? So that will somehow promote the fat oxidation. And high muscle glycogen, if we have a high muscle glycogen stored, then we less rely on the fat utilization during the later stage. Similar mechanism, right? High glucose oxidation will produce a high concentration of acetyl-CoA and marino-CoA, and inhibits the fatty acid transporter and oxidation, right? Less rely on fat utilization. Okay, so let's take a 10 minutes break. Okay, so I think there's a mistake here. I want to make collection. Thank you, Karen, for pointing that out. Actually, this is the fructose 6-phosphate, right? So glycogen is break down to glucose 1-phosphate and then converted glucose 6-phosphate and then enter the glycolytic pathway, right? So then should be the fructose 6-phosphate, right? Okay, so and here just I think additional, the detailed description of the how muscle glycogen store affect the fat utilization, and this under the situation that the muscle glycogen depletion means that we don't have enough muscle glycogen store, and what happen is that the pyruvate dehydrogenase will be decreased, right? And that will lead to less acetyl-CoA produced, that you have less malonyl-CoAs formed from the ACC enzymes activities, and then you will lead to increased CPT1 activities, and then you have a reduced acetyl carnitine and increased carnitine level, and most importantly that you have decreased fatty acids transported, increased fatty acid transported into the mitochondria. So that means during the low muscle glycogen store that you body try to promote muscle to utilize more fatty acids. And but we know that during the high intensity exercise, the ability of fat utilization actually decreased. We're going to talk about the reason why fat utilization decreased, because one of the reasons is availability of rice. Although you try to increase the utilization of fatty acids, but the availability of fatty acids actually decreased. So that is limitation that you cannot utilize more fatty acids. And if we have a higher muscle glycogen content, then we're able to utilize, glucose as the energy, and we reduces the fat utilization. That means we less rely on fat utilization during the high intensity exercise, right? So muscle glycogen store is very important. That can significantly affect the exercise performance, right? Particularly in the later stage, we need energy, ATPs, and so that's very important. The high muscle glycogen content can increase the exercise performance. And also some kind of concept clarification. We talked about the lactate acid production, right, and which is related to the fatigue, muscle fatigue. So, and we just wanted to know where is lactic acid produced, in which type of muscle fibers, and what type of exercise. And so basically the lactic acid is produced during an anaerobic exercise, right? Or in the anaerobic muscle fibers, particularly in type 2X fibers, right? It usually does the anaerobic metabolism. So most of the lactic acid is produced from the type 2X fibers, and of course is from the partial glycolysis of glucose or anaerobic glycolysis of glucose, right? And the second concept is the exercise intensity. We know actually depends on the needs of ATPs, right? The more muscle contraction cycles, and you need more ATPs. So, and defined based on the oxygen consumption. You need more ATPs, then it means you need more oxidation of the nutrients, the fatty acids or glucose, so you require more oxygen. And usually the exercise intensity related to aerobic exercise, right? And utilization of a carbohydrate and fat. So anaerobic exercise, basically we mentioned that earlier, that the creatine, phosphate, and carbohydrate and glucose are the main fuels for anaerobic exercise. And of course, fatty acids will not be able to use for anaerobic exercise, right? Because of the lacking of oxygen. And in the 2X fiber, you also have a lower mitochondria, right? So both, kind of combination. And aerobic exercise be able to use both fatty acids and carbohydrate as energy. So how to increase muscle glycogen store, since it's very important, right, for performance. Of course, we can provide glucose from exogenous sources. We eat glucose, right? To eat carbohydrate food can provide more glucose and particularly to store in the muscle. And depend on the timing. If you just right before game, then you drinking energy, drinking fructose, continued drinking probably is more useful, because you drink you get the carbohydrate glucose immediately from drink, right? Can be immediately used by during the exercise. So that can save some glycogen, muscle glycogen, for the later use during the exercise, right? And also energy bars. You can maybe a couple hours earlier before the games, that you can eat energy bar to get more carbohydrate load. Can also be used during the early stage, and also save the glycogen for the later stage, muscle glycogen. The question is why increasing, muscle glycogen stores important before the race. We just talked about already, right? That because the ability of muscle to utilize fat is decreased during the moderate to high intensity exercise. So high glycogen stores can make the muscle rely less on the fat utilization during the high intensity exercise, right? Okay, now let's explain the reason why fat oxidation can be increased from rest to the moderate intensity exercise, but decrease during moderate to high intensity exercise. So let's talk about the first period, increase during from the rest to the moderate exercise. Fat utilization is increased because of the increased fatty acid availability, right? The adipose tissue is a major source of fatty acids, and we know that during exercise, catecholamine levels increase and insulin levels decrease. So this kind of combination combined together, work together to activate the HSL activity in the adipose tissue to break down triglyceride and these fatty acids. And it also can break down the triglyceride inside of the muscle, right? So to increase, fatty acids availability, this is one reason, and why the fat oxidation can be increased during the exercise. And also because of the capability of oxidize the fatty acids is increased due to this important pathway mechanism, right? Exercise can increase the AMP to ATP ratio. It can activate AMPK, which increase, decrease the ACC activity and decrease the melanocortin production, and increase PCPT1 activity, so that will allow the more fatty acids to enter the mitochondria for oxidation. So the two reasons, one is availability of the fatty acids increase because of the catecholamine levels increase and decrease insulin level. And second is because of the AMPK level, AMPK activities increase, so then can promote the more fatty acids utilization, right? Transport and utilization. So for these two reasons, the fat utilization is increased from rest to moderate intensity, right? And now the reason for why fatty acids oxidation decreased from moderate to high intensity when the exercise prolonged, the intensity increased further than fat utilization, the ability to utilize fat actually decreased because lower fatty acid availability in the mitochondria, right? So remember the fat oxidation the fat and carbohydrate oxidation during the early stage can make more can make more acetyl-CoA molecules, right? And acetyl-CoA is increased, then can increase conversion of acetyl-CoA to malonyl-CoA. So malonyl-CoA level will be increased during the later stage of exercise, which can inhibit the CPT1, right, activity, and inhibits the fatty acids flux into the mitochondria. All right. So now let's talk about the specific type of exercise. So aerobic exercise, marathon. So marathon is an aerobic exercise. It runs like 26 miles, right? It takes about between 2 and 3 hours, depending on the runner, right? And energy expenditure, so running a one marathon requires the 2,868 kcal energy, and it needs to burn 750 grams of carbohydrate or 330 grams of fat in order to get 268 kcal energy, right, for marathon. And our body only has a 400 to 900 grams of carbohydrate on board, right, in the fat condition. And I mentioned, running a marathon, only half of the body muscle that involved. So that means we need how much? We only have like 200 to 450 grams of carbohydrate available, right, to make energy. And that definitely less than requirement, 750 grams of carbohydrates needed. So that means that running a marathon, we cannot just only utilize carbohydrates. It's not enough for energy. So we have to utilize other energy like fatty acids. So in running marathon, we use both carbohydrate and fat as an energy. So how can we know, what type of energy fuel that muscle is utilized? So we have a specific method can estimate muscle fuel utilization, which is called respiratory quotient, RQ. So RQ is a way to evaluate or estimate the metabolic mixture, during exercise from measure the gas exchange in lung. So we can measure how much oxygen is inhaled and how much CO2 is produced. And then based on this CO2 and oxygen ratio, we're able to estimate, what type of fuel energy be used. So how does this work? We know that the carbohydrate, glucose, amino acids, and fatty acids, they have different chemical structures, right? So complete oxidation of the molecules of glucose, fatty acids, and amino acids actually require different amount of oxygen. Here's the equations for calculating the RQ. So RQ refers to the ratio of CO2 production. So how much CO2 produced to how much oxygen is consumed, right? So this is the ratio. This is the equation for calculate RQ. And for oxidation of 100% of carbohydrate, RQ will be 1. So you can see this, the equation. So glucose usually have a 6 carbon, 12 hydrogen, and 6 oxygen, right? And it requires 4 molecules of oxygen to complete oxidize glucose and generate 6 molecules of CO2 and 6 molecules of water. So RQ is 6 molecules of CO2 divided by 6 molecules of oxygen, so it's 1, right? So if we oxidize 100% of the carbohydrate, the RQ should be 1. And how about the 100% of the fatty acids? Let's take the palmitate as an example. So palmitate has 16 carbon, 32 hydrogen, and 2 oxygen. And it requires 1 molecule of fatty acids. Palmitate is oxidized, requires 23 molecules of oxygen, right? And produces 16 molecules of CO2. So you can calculate the 16 divided by 23 is around between the 0.69 and 0.73, so around it like about 0.7, right? So if we utilize 100% of fat as the energy, then RQ will be around 0.7. So how about we utilize like mixture, energy fuel? So some of glucose and some of the fatty acids. Then the RQ for this mixture of energy fuels would be what do you think would be the RQ would be with what kind of range? It should be between 0.7 and 1, right? So if we utilize the mixture of energy fuels, carbohydrate and fatty acids, then RQ would be between 7 and 1. All right. So, and for protein, because protein chemical structure is a little bit different, from the fatty acids and glucose, right? It has nitrogen. So, so for protein, RQ usually is around 0.818. And here just the example for you guys to based on the RQ and to estimate what kind of energy fuel that muscle use during exercise. For example, for a marathon, right? For a recreation marathon runner, we measure their RQ and at the first 30 minutes running. So the RQ is about 0.9 to 0.1, up to 1, 0.9 to 1, right? And then after 2 hours running, and you measure the RQ again, you see the RQ actually changing to 0.8 to 0.85, so RQ is decreased. So the question here is, what does this information, RQ information, tell you about the fuel utilization? For example, during the first 30 minutes, what type of energy fuels this marathon runner use? More carbohydrate, right? Yes. And how about after 2 hours? Yeah, fat, right? Because RQ reduced, so that means after 2 hours, the runner utilizes more fat compared to the first 30 minutes period of time, right? So you try to remember this and be able to calculate, be able to estimate what type of energy you use based on the RQ, right? Any questions? Yeah. All right. So I think that we just stop here for today, and then we have a quiz. Oh, question? Yeah. Mm-hmm. Yeah. Oh, that's a good question. So I think that during the exercise, most the energy fuel that the runner use is the carbohydrate and fat. Usually we don't, our body, I don't think our body uses much protein for energy for exercise, right? So the protein utilization pretty kind of constant. So usually just, carbohydrate and fat utilization that changes RQ.